Second camera.
What are you doing?
Dude, you told me to try and pull up the games. I'm trying
Okay, you're live.
You want
Hold on, we're trying to play the game.
Okay, it's fine. Okay, after much anticipation, we're ready. So, we did Angry Physics Bird Style. My name's Taylor Medioli.
And I'm Megan Okuda.
And I'm Gianni Piro.
Okay, so I'm sure many of you have been, are, or will be addicted to the game Angry Birds sometime in your life. It's a very simple game. You just try to slingshot these little birds over into these green pigs, and they're usually surrounded by wooden or metal barriers. And there's all crazy kinds of point system. You can obtain maximum points by achieving combos or using minimal birds to kill the little pigs. Okay, so basically that's a still shot of your main objective. See the green pig over covered up by the wood. The little bird goes into the slingshot. You pull it back at your desired angle and power. How far you pull it back is the power angle, obviously up and down. And then you release it and see if you get to the green pig.
See if you get a nice projectile motion. Okay, so the first qualitative observation we had was that there was no acceleration in the x direction, which is good physics because due to the laws of parabolic motion or projectile motion, if there's acceleration in the x direction, it's really not going to be a parabolic motion. So there was no acceleration in the x direction because you can tell, it's kind of hard to see on the screen right now. It would zoom in if we had it right, but there's little white dots and it tracks the motion of the bird, and the little white dots were spaced evenly. They were spaced evenly throughout the entire motion. So it showed in the x direction that the speed was the same throughout the entire motion because the vector didn't get longer in each stage of that motion. So there were equidistant velocities, no x direction acceleration. There was a non-zero velocity. In projectile motion position changes in the y. It changes in the x, but it's constant over the x. It doesn't change. It changes in the y and has acceleration in the y due to gravity.
Okay, and our second qualitative observation had to do with the velocity of the bird. This was found during the launch. We wanted to see if the speed of the bird was the same as it would be in real life. So using kinematics, we calculated the velocity of the bird in the game, and it ended up being 5.1 meters per second. And using Google search engine, we found that the speed of a bird in projectile motion, or in the average speed of a bird in flight, is actually 14.4 meters per second. So this is bad physics in the game, because obviously the velocities of the bird didn't match, but it was good for the game because if the bird was actually traveling as fast as it should in real life, then you wouldn't be able to see it go across the screen because it was too fast. So like I said, it was found during the launch. It was bad physics, but it didn't agree with the laws of physics, but it was good for the game because you wouldn't be able to see the bird.
Okay, next we're going to show you our calculations that we did for finding if the gravitational force in the game was equal to the gravitational force in real life. So, what's this mouse again? I forgot. So here we have a diagram. It's a still screenshot of the kind of situation that we used. Our known values, we measured the height of the slingshot using a ruler, and in the screen it was 4 centimeters. We measured the height of the bird, we guessed the mass of a bird using Yahoo Answers. And then we calculated the angle of the launch using a protractor. And then using all these known values, delta x and delta y, the maximum height of the bird at the top of the launch using the velocity dots, we were able to calculate a couple of different things. But first we had to scale it to real life. We found on Yahoo Answers again that the average size of a cardinal, which is about roughly the size of the bird that we decided to use in the game, is actually about 27 centimeters. So for scaling purposes, we divided the actual size of the bird by the size of the bird on the screen and decided that we needed a 30-to-1 ratio for the scale. So that changed our known values a little bit, and you can see that in bold afterwards. So using all of our known values and the time that it took for the bird to launch into the barriers, The first thing we solved for was the change in x. And we did this using the kinematics equation. Delta x is equal to the initial velocity times the change in time plus 1/2 of the acceleration in the x times the change in time squared. There's no acceleration in the x direction, so that term actually canceled out. And we found that the change in the x direction was going to be 4.4 meters. We solved for the initial velocity in the x direction, and we found that it was 4.4 meters per second. Using the initial velocity in the x direction, we calculated the initial velocity of the actual launch itself. And we did this using the equation the initial velocity in the x is equal to the initial velocity times the cosine of the angle that it was launched at. So it was launched at a 30-degree angle, so by manipulating the equation again, we found that the velocity of the actual launch itself was 5.1 meters per second. And we manipulated it one more time to find the initial velocity in the y direction. And that equation is the velocity in the y is equal to the velocity vector times the sine of the angle that it was launched at. And that was 2.6 meters per second. And then after finding all of this, we were able to solve for the acceleration in the y. We did this knowing that at the top of the launch, at the very maximum height, the velocity in the y would be equal to 0. And so by manipulating the kinematic equation, velocity squared is equal, or final velocity squared is equal to initial velocity squared plus 2 acceleration in the y, change in y. We were able to find the acceleration in the y direction. And so after doing all of that, it ended up being negative 4.5 meters per second squared, which is about half of the value of gravity. And then the last thing we did was calculate a percent error, taking the actual value minus the measured value over the actual value. And our percent error was about 54%. Is the oh, sorry, dog. Yeah.
Okay. Alright, so for our qualitative interpretation, we did a percent error, and that was back to the 5.1 meters per second and the 14.4 meters per second, and we ended up getting a percent error of 64.6.
Cool. So we'll go on to the conclusion now. It's kind of hard to read because it's small, but there was some bad physics and some good physics with the game. Some of the good physics was that they showed that the acceleration in the x direction was constant. They were able to show that by the little white dots being spaced out just the same as it went through the entire motion. Some of the good physics, or that was the good physics, some of the bad physics was that the bird actually flew much slower than an actual real-life bird would fly, but that helped the game. They took that into account when they made the game, and it helped the game a lot because you wouldn't be able to see the bird fly across the screen, and it would be over really quickly, and that wouldn't just be fun for the user. So they took that into account, which is a good thing. It helped the game out a lot, but the bird didn't fly as it was supposed to, and a bird flying that slow at that mass would never be able to knock down an entire house. So that was also pretty bad physics to be able to knock down an entire house and kill pigs when you're flying very slow and have a very small mass. The first one you're thinking about.
And then there's references in that tiny little bubble there.
So way down there.
Sorry.
Questions for this group?
Sorry the formatting wasn't. It was just Prezi let us know.
Couldn't figure out how to get your Mac to talk to them.
Yeah, to computer.
Okay. Nope, come on.
Fire away.
Question, somebody. Yes.
Sure. Was the physics distracting in the game?
No, Angry Birds is fun.
I don't think it was distracting. I think that even though there were good and bad portions of it, like Yanni said earlier, it added to the gaming experience because you were able to watch the whole motion of the bird as it hit the pigs, and then it was still exciting to watch the birds knock down things. So even though there weren't accurate portions of it, it added to the gaming experience.
It made the game better not having good physics, because if you were to have real life situations and good physics, like I said, the game would be over really quickly, and you wouldn't be able to knock down a house, so you wouldn't have a game unless you did some bad physics, so it actually helped the game out a lot.
Any other questions for this? All right, thank you. Group 3 should go up there and try to get voted up.
We're sorry. We apologize.
This thing's happening.
Yeah, we can try that. We'll close the game.
No, it was really.